Today during class, we started talking about 6.5. We realized that I wasn't able to finish everything within one class setting because we take some time for the quizzes. But I really feel like we need sufficient time for class discussion. So I want to move some of the topic, my explanation of the topic in the section, maybe it can move to an online video that you can watch. We finished most of it, 6.5, and so I felt like we should have it finished in one day. So next time we'll review and we'll move on to section 6.7. All right. So the 6.5 focus on simple regression, and we're trying to look at relation between two variables. In class, we're talking about this. This relation can be represented by a calculation of the expected value of y, given that we have information about x. So if we already have information of x, and if x and y have a linear relation, then e of y given x can be represented by a linear function such as alpha plus beta x. Say if you collected a sequence of number for both x value and y value, we're trying to figure out the possible relation between x and y, assuming that relation is alpha 1 plus beta x is the e of y given x. Then the actual y value is the last line of the formula. The actual y value equal to alpha 1 plus beta xi plus epsilon I. This epsilon I represent the error when we're using the predicted value to represent the y value. There may be a little deviation. So that's why we're saying yi, it does not equal to exactly alpha 1 plus beta times xi. It equal to this plus a little deviation. So that deviation, we assume it has a normal distribution with variance sigma square. Having that, we can model this with a computer code, this we mentioned earlier. This is the same code that we had for the example of this section. This is the example. So you see the x value is 7, 74, 72. The y value, there are 77, 94, 88. I believe these were test 1 score and test 2 score for class. So having those number, so here are the x value and y value, and we want to find the linear model. You can run this with the coding on the computer and to find out the linear model. And we're going to go through this later. And then this is the possible coding to calculate the model. It will be like a number plus another number times x, and kind of the linear model going to produce that formula for us. In the outcome of this running the function lm, you will find out the y-intercept, the intercept, and the slope. It's going to give you the slope and the intercept, and you can build your own model. You can plot this linear model that's produced by the R coding, and you can add a line. The linear model can be, which is an equation of a line, can be drawn on top of the scatter plot. You can also use the residual from the linear model to calculate the sigma square, which is summation of square divided by sample size. In this example, the sample size is 10. All right. We went then there are a portion of the class we're talking about how to figure out the linear regression model using the maximum likelihood method. So assuming the underlying model have this linear format, then we need to figure out the alpha, the beta, and the sigma square that we assume to be the case for the distribution of the error term. So epsilon I is random because xi and yi is random, and we collect the data for it, even though we have those number already. But before we collect the data, they're random. All right. Assuming this is something that we're going to calculate, we can construct a likelihood function L alpha beta sigma square. And the way we construct this model is multiplication of all the density function. This was using the normal distribution density function. And our random variable is yi minus the predicted I, which essentially is epsilon I squared. Though we're not calling it that way because we really need to have the alpha beta in the likelihood function. So in this function, we have the sigma square, we have alpha and beta. So we have three parameters. So this will be a scenario to have three parameters in order to maximize the likelihood function. And then we realize in the likelihood function, this likelihood function have negative power. So we make the ln of the likelihood function negative. Therefore, the outcome is now positive. In order to maximize the likelihood function, we will be minimizing the negative logarithm function, and realize that the term that we're trying to minimizing on the right side, almost all of them are in a increasing order. So because a logarithm ln is increasing, then the function, if we're calling the numerator h alpha beta, then this function is also increasing with respect to. So all we have, so the in that nature, because of that, having a single increasing decreasing behavior, all we have to do is minimize the h function. All right, so in order to minimize that part, we just name h alpha beta. In order to minimize h alpha beta, we will find this partial derivative and set the partial derivative equal to 0. So this is like a multivariable calculus. We've done that in Calc 3. So a dh d alpha set equal to 0, dh d beta set equal to 0. Now, when we're setting dh d alpha equal to 0, we find out the summation, right? Summation, see that because the summation xi minus x bar, this entire summation equal to 0. And then we have the first term, the summation of yi minus n alpha has equal to 0. Then the alpha equal to summation of y divided by n. So then basically alpha has to be y bar, the mean of y value. And that kind of kind of explain the original setup. We set up the yi equal to alpha plus beta times x minus x bar. And then with that model being set up, we realize alpha has to be y bar. And another different partial derivative is dHd beta. We set the dHd beta equal to 0. And then we're able to solve for the beta. Beta, you can move the beta term to the right and divide the coefficient. We have this beta formula. So this beta can be calculated this way. Now, having beta that way, we can distribute the full term and cancel some of the common terms, which end up giving us a submission that's slightly more complex. Right, having a maximum likelihood estimator for beta, and having a maximum likelihood for alpha. Alpha is y bar, beta is this summation divided by this summation. And now we're up to try to figure out appropriate model for sigma, right? To calculate the sigma square, which is the variance of the normal distribution, we're going to calculate d negative ln of L divided by d sigma square. Well, this is calling sigma square, but you can call, instead of sigma square, you can call that theta. That way you can forget about the square part, realize that's a single variable, not a variable square. So when you differentiate the ln part, you have n over 2 times sigma square. When you differentiate the h over 2 sigma square, you have 2 sigma square square. This is a single variable squared, assuming sigma squared is a whole, like one number, instead of thinking of it as a number squared. So anyway, with that, we set equal to 0 and solve for sigma, and that gave us the sigma squares estimator. And the one that I labeled as the grain, 1 over summation of the error square, summation of the error term square, or you can call that summation of the square residue. All right, now we have an estimator for alpha, estimator for beta, and estimator for sigma square. We're now up to try to, and then there's another formula for calculus. I really prefer the more symmetric formula that has 1 over n summation of sigma square. All right, this term y minus y hat, or y minus alpha hat minus beta hat times x minus x bar, is y minus the predicted y. This is called a residue. When so there's a I, because we really got n of this value, so we have epsilon 1, epsilon 2, epsilon n, because I takes on 1, 2, 3 until n. So there's n residual number there. So this is n number we can plot. You can actually plot this n residual number back to back with the x value as a residual plot. And as I said, the residual plot should have all these dots above and below the horizontal line, since the mean is supposed to be 0. All right, this is a numerical example that we had earlier. We did it with R, and now we're doing it by hand. This is our data set. And we're going to have the summation of the y value, which is 813. You can see 813 divided by 10 give you the predicted uh, coefficient alpha. The coefficient beta, we follow the formula that we mentioned earlier, which is this beta at the bottom. You have summation of xi times yi minus 1 over n summation of xi times summation of yi divided by summation of xi squared minus 1 over n summation of xi squared on the outside. So this, the formula for beta hat at the bottom, the one on the right is the one we follow in this calculation. So you will have summation of xi times yi, and this is the last number in the column for x times y, and that's summation for xi times yi. You also need summation for x and summation for y. That's 683 and 813. And that's also in here, 683, 813 divided by 10. So that's the numerator part of it. Denominator, we have summation of the x squared. Summation of x squared is 47405 minus summation of the x, which is 683. And that is multiplied to itself. You can see 4704. 405 minus 683 times 683 over 10. That's the denominator for beta. So following the formula we had in the last row here, we're calculating the beta by hand. So we should be able to do it both ways, ourselves with a formula in the book, or with the R coding should give you the same beta. That's the same value. And lastly, we should be able to get the x bar is also part of the formula. Essentially, we have x bar and y bar in the linear regression equation, and also the slope is a 0.72. The beta represents the slope. All right, so these are source of some of the data we're using in this example. Now, you can also find out the alpha beta. This is a equation produced by Minitab. Instead of having the point slope formula that we had at the bottom of this page, we can have the 81.3 plus 0.74 minus 683 calculated, and you end up getting the 30.6. That's really what will be produced by R if you're using the R coding for this example. All right, the sigma square can be calculated by the summation of square, which is on this page. At the bottom lower right, right lower corner, 217.7, that's the number. That's the summation of square, and you want to add it, summation square divided by 10. That's the variance for the error term, variance for the error term. So that's using the software. We should be able to get a similar answer. This is a residual plot. Like I said, we will plot all the residual. We have the residual in this, that is in the y minus y hat column. So negative 5.5, positive 847, 3.995. All these numbers can be plotted in here. So on the horizontal axis, we have the x value. On the vertical axis, we have the residual value. And you can see there are 4 of them above, there are 5 of them below, but some of them are closer. So the overall average has a mean 0. This is a residual plot, and that's like a reasonable residual plot. If the residual plot is not symmetrical around 0, then something is wrong. And that's another way to detect some problem with the linear regression. All right, distribution of the estimator. We got an estimator, which is y bar, and what kind of distribution does this estimator has? So really, we're talking about what is the distribution for alpha hat. What's the distribution for y bar? So number one, you want to find a mean. The mean of this is summation, expectation of 1 over n summation of yi, and then you want to, the mean of this term is 1 over n summation of the expectation of yi. Remember, summation of the expectation of yi is actually alpha plus beta times xi minus x bar, and then this summation actually equal to alpha. And so that shows the average value for alpha hat is alpha. That means the alpha hat is unbiased. So it's a good estimator. It's an unbiased estimator. Another thing is to prove that the variance for alpha hat is actually sigma square over n, which kind of makes sense since the um, variance of yi is sigma square. So we have 1 over n, 1 over n squared, and then there's summation of variance by I. So it follows some of the summative property of variances. All right, we would also want to, well, another thing is alpha hat is normally distributed. The reason for that is because the yi is normally distributed. Okay, another one is we want to find out the distribution for the estimator for beta, which is beta hat. So we need the formula for the beta hat, which is right here, and then we want to find the expectation of it. Which involve knowing the expectation for yi equal to alpha plus beta times xi minus x bar. This calculation gave us a final answer of beta. And that also proved that the beta hat is a unbiased estimator. And the variance of beta hat is equal to, again, the coefficient is that numerator divided by, that looks like a probability, right? The numerator divided by the summation times the variances. And then because the summation on the outside would cancel the summation on the inside, well, cancel one of them. And then the one of the summation of square is left after one of them is canceled. So you can see the summation, the variance of beta hat is variance of the population divided by summation of xi minus xi squared. We're going to revisit this again later in chapter 7. So this is the point estimate right now, and we want to find out their distribution, and later we want to do a interval estimate. So this we're going to and look at this one more time later. So here's the mean and variance for alpha hat. This is a mean and variance for beta hat. Both of the estimator are functions of random variable, and we want to find out the mean and variance of those variables. All right, so here are the coding of the same number, and we should be able to repeat the same calculation as showing the as being shown on the computer in the example. So we enter the x value, enter the y value, figure out the linear model, and put the result of the linear model in the storage set in a number in the data set A. So A carry and the many of the outcome. If you want to look at it, run this, you're gonna see what A has. If you ask computer to print the A, and that's what we're doing here, printing the A. So you can see calling the LM function, and then the outcome is giving the intercept, which is 30.6, and the slope is 0.74, which kind of is the same as what we already have after we run the coding. 30.6 and 0.74, that's the result from Minitab. And we got 0.74 for beta, but the alpha is 81.3. But those can be calculated by hand if you wish to get to that. You can plot the scatter plot, which we did. This is scatter plot. On the scatter plot, we add a line, which is a line that we get from the linear model. And then you can get the residual from the A. A contain more than what we're displaying. So here in the coefficient, in this displaying of the A, you only see this equation, But if you want to see more, you can summary of A. So you can ask the computer to show you more information that's contained in the outcome of the LM function. So that way it actually shows more. And this is actually useful for what we're going to do in section, in chapter 7. All right, so you see, it shows you the residual, even shows the distribution, the 5-number summary of the residual data set. It has a coefficient which involve the intercept and the slope. It also have the standard error of the intercept and standard error for the calculation of slope. It has a t-value. It has a probably the p-value. So it definitely contain more information when you call the summary of the outcome. So really the linear model's outcome is being stored in A, but unless you call the results, when you just say A, it only shows you the final result, the linear model. After the plotting, this is also pulling the residual data from A, and the summation you can square this and then find the summation of square and then divide by 10, and then we're getting a number of 21.77, which is the same as what we have in this R coding. So that residual 21.77, we're getting the same result as what we have here in the table, the 217.7. I'm calling, I did say the wrong number last time. 217.7 is at the bottom corner, bottom right corner, and we're using that number to calculate the variance of the residual, which we get the same number here in this process. This is just a scatter plot alone. Oh, this is a residual plot, right? Right? The same residual plot as you would say here. It's plotting the residual plot. And it's exactly same picture. So basically, many of the things that we see being worked out in in the textbook, we're able to do it with R. Um, all right, just want to repeat that code so you can see how it works out. All right, this is a homework assigned for 6.5. I hope that suffice. And I think we have only a little bit left over in class. I don't want to have to redo everything next Monday. So I want to post a short video. Just want to explain it one more time. All right, please work on your 6.5 homework and let me know if you have any question next Monday. I'll see you next Monday.